Hello everyone, my name is Joseph Boy Ukeme. I'm here to present our paper titled Real-Time Fault Detection and Diagnosis of Cyber-Physical System Faults in DEVS. The co-authors of this paper are Christina Ruiz-Martin and Gabriel Weiner. We are from Carleton University. So there is an ongoing smart revolution. So we see these days that we have smart devices everywhere, smartphones, smart cars, buildings, cities, etc. Now these kind of devices makes it interesting the kind of hardware and software requirements we have. So software now includes tools for data management, decision making and learning algorithms. Hardware includes more intelligent sensing and actuation. So the state of the art means we have more sophisticated infrastructure, and this kind of sophisticated infrastructure means that cyber physical systems are more fragile, so they are prone to faults and failure. And then we need intelligent ways to handle these kind of issues that come with the trends of cyber physical systems. So our motivation is from the fact that modeling and simulation is a viable method to handle the complexity and heterogeneity of cyber-physical system design. However, formal modeling techniques have several limitations. For example, they cannot explicitly model the environment, and because you can't explicitly model the environment, faults are bound to occur. Now, these methods do not formally define how we handle these faults, right? So fault detection and diagnosis methods are not formally integrated into modeling techniques. Now, if you decide to integrate any of these techniques or to improve the reliability of CPS designed with formal method, it is difficult for several reasons. For example, real-time constraints, it's computationally intensive, you have memory constraints, among other things. Now, why is cyber-physical system fault detection an issue? Now, if you don't have the proper fault detection and diagnosis method, you could get escalation of simple faults into catastrophic failure. You could have fault that propagates within subsystems, and this is like a typical characteristic of cyber physical systems. You could have unreliable automation processes or procedures which could lead to catastrophic consequences. Now, these factors has necessitated the development of an intelligent and easy to use fault detection technique, and this is what is presented in this paper. Now, our approach can be summarized in this slide. So we have on the figure on the left is an abstract design of a abstract figure of a cyber physical system. So we have the physical components, we have the interface, and we have a control system which could be hardware or software, which we call the cyber components. So our approach is simple. So first of all, we want to classify what the faults mean. We want to define these faults within a formal modeling framework. Then we go ahead to develop our method for real-time fault detection and diagnosis. Then after that, we'll develop methods to guarantee fault tolerance, typically by fault accommodation, which is part of our future work. Now, to define what a fault is, we took a taxonomy, like I said, and we classified those faults into three different aspects, right? So we have sensor faults, actuator faults, and control system faults. Now, the next step was that we related these faults to the modeling framework. Like, so what does the fault in the physical system mean in the modeling methodology? So, for example, we say sensor fault maps to a violation in the input set of the DEVS model. That being said, a fault in a DEVS-based cyber-physical system has occurred when the behavior of the cyber-physical system does not conform to the specification that we defined in the DEVS model. Now, this is our scheme to detect and diagnose faults in cyber physical system. Now, the scheme was defined to satisfy several requirements, which handle the key challenges of fault detection and diagnosis. So this scheme would correctly identify faults, and it's able to distinguish between a fault, a noise, and an uncertainty. It's going to be able to isolate faults within a complex cyber-physical system. It's going to be able to manage multiple faults that occur simultaneously. It's going to prevent faults within subsystems from escalating into major faults, and it's going to consume minimal resources and ensure speedy computation. Now, the main components of this fault detection and diagnosis scheme include the discrete event control software, the supervisor, and the knowledge base. Now, from the figure on the right, it's the scheme and we'll describe it. So first of all, when we have a cyber-physical system, we're going to try to define a model of the cyber-physical system. Now, having defined this model of the cyber-physical system, we can anticipate some faults that can occur, and we're going to put those faults in the knowledge base. When we have the model, the next step will be to try to simulate this model in a simulation environment. Now, when we simulate the model, we have a model of the environment and we have a simulation model. We're bound to see that there are other faults that could occur. Then we're going to move those faults into the knowledge base. Now, you see that while we simulate, we could also make modifications to the original model, and that's why there's an arrow going back to the original DEVS model. So information obtained from simulation would have to be updated in the model itself. Now, when we're satisfied with our simulation result, we're going to put these models into a target platform. Now, we're going to do physical tests and experiments, and we're going to be able to see more faults, potential faults. We put them in the knowledge base as well. Now, the supervisor and the discrete event control software are also part of the cyber physical system. And if you look here, we can find some things that would allow us modify the original model even when we're testing on the target platform. That's why you see an arrow going from the discrete event control software to the DEVS model. Now, during the operation of the cyber physical system, what happens is this. So the discrete events control software is where the control system sits, right? Now, whenever there is a fault, it believes that the specification has been violated, which could be a fault or an uncertainty or noise. It's going to send a message to the supervisor, and the supervisor would then check with the knowledge base with that message. We call the message a fault message. Now, when the supervisor checks the fault message, the knowledge base, if it's a yes, the knowledge base replies a yes or a no. If it replies with a yes, the supervisor is going to send a message to this DECS, and this DECS would activate whatever fault tolerant algorithms that we define within the control system. Now I'm going to explain the different components. So the discrete event control software is basically made up of atomic models with state variables. Now each model would generate a fault message, like I said, and whenever this happens, whenever a specification appears to be violated, so this message is sent to the supervisor, and the supervisor knows what to do with that message, right? So within the discrete event control software, multiple faults can happen at the same time, and each of these models would send their outputs to the supervisor. The discrete event control software also has an input port where it can receive a message for fault accommodation or handling from the supervisor as well. Now, this is the next component is the knowledge base. So the knowledge base is defined to handle several requirements. So the first thing is that we want to minimize memory usage. We want to allow for quick search. We want it to be mutable because, like you saw in the scheme, the knowledge base evolves through the life of the cyber physical system. We want it to have a unique fault identity, which we call the fault ID. And the reason for the fault ID is to ensure that we can isolate faults within a large cyber physical system. On the right here, what we have is the knowledge base. Now we can see that there is a fault ID and there is the frequency of occurrence. Now this is just a description of what it means, right? For example, A1 means that a fault indicated by A1 is out of range, right? And A1, B1 means A1, B2 are out of range, and you can see the frequency of occurrence that happens here in the knowledge base. Now for implementing this knowledge base, you could use any convention of your choice that allows the unique identification of components as the fault ID, and then you could implement it in a database of your choice. For us, we tried different possible implementations, right? We used the flat file, we did the Bloom filter, and we also tried the standard hash. Now the next component is the supervisor. Now this is a simplified algorithm that describes the operation of the supervisor. Now the supervisor sets priority for each atomic model, right? So that when it receives a message from the atomic model, it can decide which of these messages to handle first if they come in simultaneously. Now when it gets this message, it's going to check if this is a fault that exists by itself with the knowledge base, and then if it's a fault, it's going to send the trigger back to the DECS. If it's not a fault, it has to hold on to it for some time that we define, because we notice in cyber physical systems some faults are not dependent on others, right? Or they are dependent on others depending on how they occur. So we pull for a short while, and then if we find that it depends on another fault, we check them together and then pull for a certain time. And if we see that in the knowledge base, we send the trigger to that atomic model. And when the time expires and we're holding the fault and no other related fault message comes in, we can discard that message as a transient fault. We increment every time, we increment the count and the frequency of every fault message that the supervisor sends back to the discrete event control software. Now we have a simple case study that we implemented to test the functionality of our fault detection and diagnosis schema. So we have 4 models. Each of them sent their fault messages. So model A15, model B54, model C20, and model D37, making 126 fault messages from the discrete event control software. Now, the total number of actual faults that the supervisor checked and validated from the knowledge base is in the table below with their fault codes. And you can see that there are only 50 of them. So 76 of these messages were most likely noise or transient faults. Now we can also see that if you look at this figure on the left, some faults occur simultaneously, right? And the supervisor was able to handle those faults based on a priority list. One more thing we can see here from the results is that if you look at the fault code, you can tell where the fault model comes from, right? So for example, A1, we can say that it's from atomic model A. So this shows that the supervisor is able to isolate where the fault has originated from, which is one of the requirements we try to meet. Now we had to consider options for scaling up our scheme, right? So how do we deploy this scheme to a larger system? So we thought about this, and we think the best approach would be a modular approach across the cyber physical system, and we can do this in 2 ways. So one of the way will be to have the complete fault detection scheme in different parts of the system, and that way we can scale it up. Another way will be to split the knowledge bases into smaller manageable units across the entire cyber physical system. Then we have one supervisor coordinate the activities between these several knowledge bases and the discrete event control software. So from this work, we presented a scheme capable of detecting and isolating faults in real time. The scheme is consistent with the DEVS formalism, so it means that it's compatible, backward compatible with other DEVS models. We've also discussed some options for scaling up this scheme. For our future work, we will deploy this scheme to a more complex case study to see the functionality. We're going to develop fault-tolerant control algorithms to respond to faults detected by the scheme as well. Thank you for listening, and I'll take your questions. If you have any questions, you can ask me or you can send me an email. My email address is displayed on the screen.